Please pause the video and try this problem. Now let's discuss this problem together. Remember that if you find that these video explanations move too slowly, you can simply try the problems in the problems document, study the solutions in the solutions documents, and if necessary, use the table of contents for each video to skip to the particular parts of the videos that cover the parts of the solutions that are giving you difficulty. Here are some keyboard shortcuts which you may find useful while you're watching the videos. Here's a summary of the solution for part A of the problem. Let's work through this solution step by step. The problem mentions the concept of friction, which is a force which can be substituted into the Newton's second law equations. And the problem also mentions the concepts of radius and velocity, which can be substituted into the formula for the radial component of the acceleration, which can be substituted into the Newton's second law equations. So we plan to use the Newton's second law problem-solving framework to solve this circular motion problem. Next, we should draw a circle to represent the object's circular path of motion inside the cylindrical amusement park ride, like so. In this problem, the person is moving in a horizontal circle. When possible, you should represent what the question is asking you for with a symbol, or in this case, a combination of words and a symbol. The problem is asking us for the linear velocity. Now, linear velocity is the ordinary concept of velocity that we usually use in physics, with symbol v and SI units of meters per second. We use the term linear velocity to distinguish this concept from the concept of angular velocity, which is mentioned in parts B and C of the problem. Angular velocity is represented with the symbol omega and has SI units of radians per second. Now, in this context, part A is probably best interpreted as really asking us for the magnitude of the velocity. The magnitude of the velocity represents the object's speed. We can represent the magnitude of the velocity with the symbol lowercase v written without an arrow on top. So we write that part A is asking us for the minimum speed required to prevent the person from slipping downwards. Now, this type of problem is actually best interpreted as asking us for the borderline speed, at which the person is right on the borderline between slipping downwards and not slipping. For a minimum or maximum problem involving whether an object will slide, the way to solve the problem is to assume that the object is on the borderline between sliding and not sliding. This problem is a minimum problem involving whether the person will slide downward. So, to solve this problem, we will assume that the speed is equal to the borderline value, and we should write down that assumption. The problem refers to the borderline speed as the minimum required to prevent the person from slipping downward. So if the speed is greater than the borderline value, the person will not slip. And if the speed is less than the borderline value, the person will slip downward. But what will happen if the speed is equal to the borderline value? Well, for a minimum or maximum problem involving whether an object will slide, the way to solve the problem is to assume that at the borderline value, the object will not slide. So, to solve this problem, we will assume that at the borderline speed, the person will not slip. Write down that assumption. To summarize, to solve a minimum or maximum problem involving whether an object will slide, assume that the object is on the borderline between sliding and not sliding, and assume that at the borderline, the object will not slide. Next, let's check that the given units are SI units. Well, yes, the only units that we were given in this problem are meters, and those are SI units. Now we're ready to work on the free body diagram. Now, we usually draw a free body diagram for each object whose mass is mentioned in the problem, but this problem doesn't mention any masses. So what object should we focus on for this problem? Well, the question for part A is focusing on the person. So we expect to apply the Newton's second law equations to the person and we need to draw a free body diagram showing all the forces exerted on the person. In our sketch, we should indicate the person's current position in the circle. Now, the problem actually doesn't specify where the person is currently located in the circle, so let's assume that the person is located at the far left of the horizontal circle. I'll draw a dot at this position to indicate that we're assuming that the person is currently located at the far left of the horizontal circle. First, we draw the vector for the object's weight. Next, we ask what is touching the object. Well, the wording of the problem makes it clear that the person is touching the wall of the cylinder. A wall is the type of thing that we treat as a surface, and a surface can exert two forces, both a normal force and a frictional force. And we know from the problem that there is friction in this problem. Because we're assuming that the person does not slip, we should apply static friction, not kinetic friction. And because we're assuming that the person is on the borderline of slipping, we will apply the maximum static friction. The person is on the verge of slipping because the static friction which prevents them from slipping is maxed out. Besides the wall, there is nothing else that is touching the person, so there are no other forces to include in the free body diagram. The direction of the weight force is straight down. Here's the rule for determining the direction of the normal force. The normal force should point perpendicular to and away from the surface that is touching the object. So, the direction of the normal force exerted by the surface of the wall on the person should be perpendicular to and away from the surface of the wall. Now remember that we are supposing that the person is currently located at the position of this dot, at the far left of the circle. So in this position, the normal force will point to the right, perpendicular to and away from the surface of the wall. So in my free body diagram, I indicate that the normal force is pointing to the right when we suppose that the person is located in this position in the circle. So the normal force will always be perpendicular to the surface. Here's a method for finding the direction of the maximum static friction force. The problem tells us that the person is on the borderline of slipping downwards. So to prevent that, the maximum static friction force has to point upwards. Keep in mind that the frictional force will always be parallel to the surface. For this problem, the frictional force is pointing parallel to and up the wall, in order to prevent the person from sliding parallel to and down the wall. Now let me ask you a question. Did you correctly determine the directions of the normal force and the frictional force for this problem? The key to getting those directions correct is to remember that the normal force will always be perpendicular to the surface, and the frictional force will always be parallel to the surface. So for this problem, the normal force is perpendicular to the wall, and the frictional force is parallel to the wall. Next, we work on the force table. In the first row of our force table, we represent the magnitudes of the overall force vectors. In this problem, we are not given a value for any of the forces. We have a special formula which we can use to represent the magnitude of the person's weight. Now, this problem does not tell us the person's mass, so we will continue to use the symbol lowercase m to represent the person's mass. Keep in mind that this symbol m does not stand for meters. Instead, it stands for the person's mass. Now remember that for this problem we are applying maximum static friction. Static friction because we're assuming that the person does not slip, and maximum static friction because we're assuming that the person is on the verge of slipping. There is a special formula for the magnitude of the maximum static friction. So let's use that special formula. The problem gives us the number 0.7 to substitute for the coefficient of static friction, which is symbolized by mu sub s. So far, we don't know the magnitude of the normal force, so we will continue to use this symbol lowercase n, written without an arrow on top, to stand for the magnitude of the normal force. So here's the result when we use that special formula to represent the magnitude of the maximum static friction in the first line of our force table. There is no special formula for the magnitude of the normal force. So, in the first row of our force table, we simply represent the unknown magnitude of the normal force with the symbol N, written without an arrow on top. For purposes of filling out our force table, we do not try to figure out how these three forces will interact with each other. We can let the Newton's second law equations figure out those interactions for us later in our solution. Before we can break the forces into components, we need to write down our axes. We should choose a radial axis that points towards the center of the circle. So if we continue to assume that the person is located at the far left of the circle, then the radial axis should point to the right. So here I've labeled the radial axis pointing to the right. That turns out to be the x-axis for this problem. And I'll also choose a y-axis that points up. That axis will be perpendicular to the horizontal plane of the circle. Label which of your axes is the radial axis. Now we're ready to break the forces into components. In this problem, the normal force is parallel to the x-axis, the maximum static friction force is parallel to the y-axis, and the weight force is anti-parallel to the y-axis. So we can use this rule to break all three of the forces into components. The weight vector points in the negative y direction, so W sub y is negative. W sub y has the same magnitude as the overall weight force, which we're representing with the mathematical expression 9.8 m. And the other component, the x component, is 0. The normal force is pointing to the right, which is our positive x direction. So n sub x is positive. It has the same magnitude as the overall normal force, which we're representing with the symbol n, and the y component is 0. The maximum static friction force points up, which is our positive y direction. So the y component here is positive. It has the same magnitude as the overall force, and the x component is 0. Remember that this negative sign for W sub y is crucial. If we forget to write a negative sign for W sub y, we're going to get the problem wrong. I recommend that you should include a plus sign in front of all your positive components, because that will help you to remember the crucial negative signs in front of negative components. Now we're ready to work with the Newton's second law equations. For a horizontal circle, such as the circle that we're dealing with in this problem, we typically need to write the Newton's second law equation for the radial component, which is the x component for this problem, and for the component that is perpendicular to the plane of the circle, which is the y component for this problem. Here we add the x components of the three forces based on our force table, and here we add the y components of the three forces based on our force table. We still don't know what the mass of the person is, so we continue to use the symbol lowercase m for the mass. Remember that we're assuming that the person does not slip downwards. Therefore, the person will be vertically motionless. The person has no motion in the y component. So we can substitute 0 for a sub y in our Newton's second law y equation. This is a circular motion problem, so we can use this formula for the radial component of the acceleration. For this problem, the radial axis is the x-axis. So the radial component of the acceleration is a sub x. We don't know yet what the object's speed is. After all, that's what the question is asking us for, so we continue to use the symbol lowercase v. The problem does tell us that the radius is 5 meters. The radial component of the acceleration always points towards the center of the circle. We've seen that on this problem, a sub y is 0. So on this problem, the overall acceleration vector also points towards the center of the circle. Since we chose a radial axis that points towards the center of the circle, the radial component of the acceleration will be positive. So this formula gives us this expression for a sub x. V squared over 5, which we can substitute into our Newton's second law x equation. Now, it may seem like we're faced with an algebraic difficulty here because we have three unknowns, n, m, and v, but we only have two equations. Nevertheless, I'm going to try to solve this system of simultaneous equations using the substitution method, and I'm just going to hope that one of the unknowns will cancel out during our solution. The typical pattern for solving Newton's second law problems is to begin by working with the equation which has a zero acceleration component. We usually begin by solving that equation for n, and then we substitute the result for n into the other Newton's second law equation. So I'm going to follow that typical pattern in my solution for this problem. So let's solve the Newton's second law y equation for n. Our result is that n equals 14m. Next, we substitute our result for n into the x equation. Remember that the question is asking us for v, so our goal is to solve this equation for v. In order to do that, we need to get v by itself. V squared is being multiplied by the fraction m over 5. The most efficient way to remove this fraction is to multiply both sides of the equation by the reciprocal of the fraction. We multiply both sides of the equation by 5 over m, which is the reciprocal of m over 5. The advantage of multiplying by the reciprocal is that now on the right side of the equation, the 5 over m cancels the m over 5. Also notice that on the left side of the equation, the m's cancel diagonally. That's a relief because remember, we were hoping that the m's would cancel out. That will allow us to solve this system with three unknowns, but only two equations. Now we can finish solving the equation for v. Our result is that v equals 8.37 meters per second. Remember, if you're trying to get rid of a fraction which is being multiplied by something else, the most efficient approach is to multiply both sides of the equation by the reciprocal of that fraction. By the way, here's an alternative solution. Since the Newton's second law x equation is already solved for n, we could simply take this result for n and substitute it into the y equation. Then we can solve the y equation for v. In this alternative approach, there will again be a step in which all the m's cancel out. Now we're ready to answer part A of the problem. I'll round the answer off to 8.4 meters per second. Make sure that you include units on your answer. Make sure that you've answered all parts of the question. For example, we should certainly notice that so far we've only answered part A, and that we're still going to have to go on to answer part B and C for this problem. Here's a summary of the solution for parts B and C of the problem. And now let's discuss this part of the solution step by step. We begin by representing what parts B and C are asking us for with a combination of words and a symbol. Now, part B is asking about the angular velocity. The symbol for angular velocity is omega. But again, it would probably be best to interpret part B in this context as really asking us for the magnitude of the angular velocity, which could also be referred to as the angular speed. And technically the symbol for the magnitude of the angular velocity is omega in absolute value signs to indicate that it's a magnitude. Part C is asking for the same concept as part B, but part B is asking us to use units of radians per second, while part C is asking us to express the answer in RPM, which you should know stands for rotations per minute. Here is a handout which contains a flow chart which shows us how to convert between some common concepts that are involved in circular motion. You can find a link to this handout in the video description box. Now, in part A of our solution, we determined that the linear speed, v, equals 8.37 meters per second. So we begin by noting here that the linear speed equals 8.37 meters per second. Part B is asking us to determine the angular speed. So now we need to use the linear speed, v, to determine the angular speed, which is the magnitude of omega. Here's the formula for converting between the linear speed and the angular speed. The linear speed, v, equals the angular speed times the radius. First, we write down the general formula. After we write the general formula, we substitute specifics into the formula. For v, we substitute 8.37 meters per second, which we determined in part A. The angular speed is what part B is asking us for, so we leave that as a symbol, and the problem tells us that the radius is 5 meters. Then we solve the equation for the angular speed, and we obtain the result that the angular speed equals 1.67 radians per second. Now for part C of the problem, we need to convert from units of radians per second into units of RPM. You should know that RPM stand for units of rotations per minute. This is really just an ordinary unit conversion, so we accomplish this part of the problem with an ordinary unit conversion process. We take our starting value, 1.67 radians per second, and then we multiply it by 2 conversion ratios in order to convert the units from radians per second into units of rotations per minute. One rotation, or one circle, is equivalent to 2 pi radians, and that gives us this conversion ratio. And of course, you know that there are 60 seconds in 1 minute, and that gives us this conversion ratio. Make sure that you write the conversion ratios correctly. For example, this is an incorrect conversion ratio. It's simply not true that there are 2 pi rotations in 1 radian. That's not true. What's true is that there are 2 pi radians in 1 rotation. What about this conversion ratio? Well, this conversion ratio is correct. There are 2 pi radians in 1 rotation, but this would not be a useful conversion ratio for this particular situation. For this particular situation, we want to write the conversion ratio with radians on the bottom of the fraction, because that way these radians will cancel with these radians on the top of the fraction. So be careful to write your conversion ratio so that the units end up in the right place, so that the units will cancel in the way that you want them to. And of course, I could make similar comments about how we have to be careful to write this conversion ratio correctly. In this case, we want to write the conversion ratio so that seconds are on the top of the fraction, because we want these units of seconds to cancel with these units of seconds on the bottom of the fraction. We can perform the calculations for this unit conversion in one step on our calculator, like so. Notice that you must put the 2 pi inside parentheses. Otherwise, the calculator will not realize that both the 2 and the pi belong together in the denominator of this fraction. So we've seen how useful this flowchart is for solving parts B and C of the problem. Keep in mind that this complete version of the flowchart from the handout also includes a formula for calculating capital T, which represents the period of rotation. The period of rotation is the time that it would take for the object to complete one complete rotation. Now we're ready to answer parts B and C of the problem. Make sure that you include units on your answers. Make sure that you answer all parts of the question. We don't just want to give the answer in radians per second, we also need to provide the answer in units of RPM. Now let's check whether our results make sense. Let's begin by checking whether this result for n makes sense. The most interesting way to do that is to use our result for n to get an expression for the magnitude of the maximum static friction. So here we can substitute 14m in for n. Remember that m here stands for the mass, not for meters. And that tells us that, based on our results, the magnitude of the maximum static friction is 9.8 m. Does that make sense? Well, the magnitude of the weight force is also 9.8 m. So we need to ask whether it makes sense that the magnitude of the maximum static friction equals the magnitude of the weight force. Well, the weight force is trying to make the object begin slipping down the wall. But remember that we're assuming that the person will not slip. So to prevent the object from slipping downwards, the downwards weight force has to be canceled by the upwards static friction force. So since the static friction has to cancel the weight force, yes, it does make sense that we discovered that the magnitude of the maximum static friction equals the magnitude of the weight force. Now, let's ask whether our results for the linear speed and the angular speed make sense. It's helpful to memorize that 1 meter per second is very roughly 2 miles per hour. So 8 meters per second is very roughly 16 miles per hour. I think that 16 miles per hour is a reasonable speed for the cylinder amusement park ride to be rotating. We also discovered that the cylinder is rotating at about 16 rotations per minute, and I think that 16 rotations per minute is a reasonable rate of rotation for this amusement park ride. Now, actually, maybe these results would be a little bit slow in real life. If you actually got onto one of these amusement park rides at an actual amusement park, I suspect that the cylinder would actually be rotating somewhat more quickly than 16 rotations per minute or 16 miles per hour. But of course, remember that we were trying to figure out the minimum velocity required to keep the person from slipping. If these are the minimum values, it's not too surprising that the actual ride in an amusement park would be spinning more quickly than this. Now let's do a recap of our solution for this problem. Remember, the normal force should be perpendicular to the surface, and the frictional force should be parallel to the surface. For a minimum or maximum problem involving whether an object will slide, the way to solve the problem is to assume that the object is on the borderline between sliding and not sliding, and to assume that, at the borderline value, the object will not slide. Since we're assuming that the person does not slide, we apply static friction, not kinetic friction. And since we assume that the person is on the verge of sliding, we apply maximum static friction. For maximum static friction, we can use this special formula for determining the magnitude of the maximum static friction in the first row of our force table. And because we assume that the person does not slide downwards, we know that the person will be vertically motionless. So we can substitute 0 for a sub y in our Newton's second law equations. Of course, we should choose a radial axis which points towards the center of the circle. Remember that on this problem, we assumed that the person was at the far left of the circle, as indicated by this dot. And then we were able to use this formula for the radial component of the acceleration to represent a sub x and substitute that expression into the Newton's second law x equation. Remember, if you're trying to get rid of a fraction which is being multiplied by something else, a good approach is to multiply both sides of the equation by the reciprocal of that fraction. This problem did not tell us the person's mass, so we had to represent the unknown mass with the symbol m. So early on, we had 2 equations with 3 unknowns. We used the substitution method to solve this system of simultaneous equations. We had to hope that one of the unknowns would cancel, and that is what happened. At this step, the mass canceled out of the equation. In parts B and C of the problem, we used this flowchart to convert the linear speed, which we determined in part A, into the angular speed in radians per second, which answers part B, and then to convert that into the angular speed in RPM. Remember, RPM stands for rotations per minute, and that's what we needed to answer part C. To convert the linear speed into the angular speed, we had to use this formula. And then to convert the angular speed from units of radians per second into units of rotations per minute, we had to use this information, which allowed us to write the conversion ratios, which we needed in order to do the unit conversion. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.